So we went to like a minute or two.
Yeah, no, it's fine. Yeah. Yeah, I'm sure I'll run out of. I'll flip the switch on my. Oh, it's on.
All right. All right. We go ahead and get started. Let people trickle in here. It's my pleasure to welcome Brant Robertson. Brant is a unique astronomer in my experience, in that he's done both theoretical and observational astronomy, and he's really been a leader in both. Brant studies distant high redshift galaxies in the early universe. His early work was mostly theoretical until observatories like Hubble and JWST became capable of testing his theories. So nowadays, I actually consider you more of an observer, but he really does both. I think you would say you're a theorist. But Brant went to college at the University of Washington, got his PhD from Harvard, and then he did a Spitzer Fellowship. Spitzer Fellowship at
Chicago.
Chicago, thanks. And then Hubble Fellowship at Caltech. Brant was a professor at Arizona, followed by Princeton, and now he's at UC Santa Cruz.
I was never a professor at Princeton. They would disown me if I had said that. I was a visiting professor at the IIS in Princeton for a short amount of time.
Okay.
But I love them. They just don't.
Great. Right, we'll get into that later over a beer, maybe. Brant has led exciting discoveries with JWST, including the most distant galaxies discovered in JWST's first few months of science, along with Emma Curtis Lake as part of the JADES collaboration. Brant even got to go on 60 Minutes as one of a few US astronomers sharing the excitement and highlights of the first few years of JWST science with the world. And so today, Brant will update us on everything that he and the JADES team have learned since then, with JWST now in its 4th year of observations.
Thank you so much. Thanks, Dan, and thank you to everyone for having me here. It's really an honor to be able to come here and you all don't need to be told about JWST. It's amazing to be able to talk about JWST-related science here. Obviously, this is the most technically adept audience in the world when it comes to talking about JWST, and so I thought I would include more of the technical information about JADES, because I think we don't talk enough about really the effort that goes into making high quality science data products for the community to use and for people in our community, especially junior people, to do science with. And so I thought I might spend a little bit more time talking about that, especially in support of finding the most distant galaxies with JWST. I want to give a brief history of the observable universe. Would you mind turning down the bright overhead light, please? Thank you. So, of course, the universe was initially very hot and dense, but it had expanded and cooled. After the Big Bang, the universe was almost fully ionized, but eventually it expanded and cooled to the point where electrons could recombine onto protons to form neutral hydrogen. At that point, the optical depth in the universe declined dramatically, optical depth to electron scattering, declined dramatically such that the photons in the universe could start streaming freely through the universe to the present day. They were in the UV at the time they were released, but we see them today in the microwave. It's called the cosmic microwave background. That happened something like 370,000 years after the Big Bang at a redshift of something like 1100. After that point, almost all of the gas in the universe was neutral. There wasn't a large amount of structure in the universe. There was only density fluctuations at 1 part in 100,000. But over time, gravity could do its thing. And those density perturbations could start growing through self-gravity to the point where you could form some nonlinear structures. Eventually, those nonlinear structures could support the formation of some first stars and galaxies. Before that time, there were no new sources of light. We call that the Dark Ages. And we think that the Dark Ages persisted for the first, say, 200 million years after the Big Bang, but I'm not going to bet any money on that right now. The first, say, redshift above 20 as a guess. The IGM, the intergalactic medium, was still completely neutral at this time. There were no new ionizing photons to reionize the intergalactic medium until you could start forming individual stars and eventually collections of stars at the intersections of cosmic filaments, dark matter halos, that could support the cooling of gas that then could condense, become self-gravitating, and start forming individual stars. The first stars that formed, some of them may have been quite massive, but of course they form in a distribution of masses, and the most massive of those stars are hot enough to release ionizing radiation, hydrogen ionizing radiation, that can ionize bubbles around those nucleated star-forming regions. Eventually, those bubbles can start to grow as the star-forming regions grow in luminosity. As those regions grow in abundance, there's more of them, and they grow in luminosity, those bubbles can start growing in size and number to the point where those bubbles can start to overlap. Once the bubbles start to overlap, the mean free path of ionizing photons in the universe increases dramatically, and that starts the ends of what we call the reionization process, where most of the intergalactic medium becomes fully reionized. And we think that reionization ended sometime around the first billion years of cosmic time, although there definitely seems to be some neutral pockets that persist to even lower redshifts, even later times in universal history. Then out to the last billion years, we think that kind of modern galaxies first started forming in abundance out to cosmic new, where the peak of the star formation rate density occurred, and then of course out to the present day. I'm going to ignore the vast majority of cosmic history in this talk and focus mostly on the epoch of what we call reionization, the first billion years of cosmic time. And so the big questions that kind of drive a lot of this field, which, I am not one of the people who originated this field. There are people like Massimo that I looked up to for a long time. I still do. And it's not that I stopped at any point in time. I still look up to Massimo. People that have been working on this for a long time. Can we find and confirm the galaxies that are close to cosmic dawn? What are the properties of the earliest confirmed galaxies? People have been looking for these galaxies for a very long time. What high redshift has meant has always been revised further and further upward. It's been a long process. A lot of people worked very hard on this. When did reionization start in earnest, and what were the sources that first got it started? And this is a question I think really has kind of been revised maybe the most out of all of these questions in recent years, and so I'm going to try to say a little bit about each one of these questions. So that's kind of what the scientific scope of the talk is. Like I said, I am going to include maybe a little bit more technical discussion in this talk than I would otherwise, because I think there are lots of people in the room that might be interested in some of these features, especially in the context of what people in the GTO team have done over the last few years. So I want to say a little bit about reionization and kind of some of the hallmarks of that process. And if you're interested in what the view of reionization and galaxy formation was just before JWST, I had a very well-timed ARAA review article that I pushed back to be a couple of times just before launch. And the idea was to kind of set the stage to say, okay, what do we know just before JWST and what are we expecting to learn? And you know, when this article was written, kind of what we knew at the time was that reionization likely ended sometime between redshift 5.5 and 6.5. And the evidence that we had from, for that was multifold. We had some evidence from fitting features in the spectrum of the Planck cosmic microwave background that from the electron scattering of the CMB, that the neutral fraction, the IGM, probably ended, it's a model-dependent statement, probably ended somewhere around redshift 7.5 or so, cosmic reionization epoch. We could measure the Lyman alpha forest dark fraction. So what you do is you go and you measure spectral Lyman alpha forest and you look for all of the pixels in your spectra that are dark. And that puts a limit on when reionization happened. And there was a limit placed at about redshift of 6 there. You could go and look for the presence of Lyman alpha emission in high redshift galaxies. So what you do is you count up the number of Lyman break galaxies that show Lyman alpha emission as a function of redshift. And that fraction increases until you get to about redshifts of 7, and then it declines again. And that seems to be an indicator that the IGM neutral fraction is going up. That tends to remove Lyman alpha out of the line of sight. There's evidence from Lyman alpha damping wings and quasars, Lyman alpha equivalent width distribution. There are all hosts of different measurements that were available at the time that seem to suggest that the neutral fraction might be changing the intergalactic medium between about redshift 7 and 8. Then what you could do is you could take simulations of the Lyman alpha forest and fit the evolving power spectrum of the Lyman alpha forest at lower redshift and extrapolate back what you think the ionization background had to be to match the evolving Lyman alpha forest at lower redshift. If you extrapolate back that ionizing background to higher redshift, you get this black curve, which seems to be consistent. So it's interesting that actually even lower redshift constraints of the evolving IGM tended to suggest that reionization was occurring at the same redshifts suggested by high redshift observations, albeit almost all of these are model-dependent measurements of the potential IGM neutral fraction changing. So JWST can potentially say something about this. Now, how do you try to answer this question? Well, you have to try to go find sources. So you have to try to count up the number of ionizing photons that are out there. You have to try to characterize the ionizing populations in those galaxies. And you have to say something about the fraction of ionizing photons that escape those galaxies. The third of those topics is very difficult to do, but people are making a lot of progress, at least on the first two. And so I'll try to say a little bit about those topics. So at the time, and I think, you know, there was a lot of wisdom in the community that I wasn't a part of, you know, that people designed surveys that really tried to go after as much as possible in the face of uncertainty, because we did not know what was going to happen with JWST on launch. So people did design a lot of geo programs, and you all selected some very nice arrays of geo programs in addition to the ERAS programs that did go after a variety of science cases. I was involved in several of these at some level, but I was especially involved in the JADES survey, and I'll talk about that. I was also on the Cosmos Web Management Committee. I was a co-I in the Primer survey. I didn't really have anything to do with CEERS or NGD. You know, there are many of these surveys out there. There were, I didn't show Uncover, I talked about GLASS, I didn't really go into much detail in the review article, but there was a lot of excitement because I think there were a lot of questions people thought that the wide array of these surveys could potentially answer. There were wide area surveys to look for large scale structure. There were very deep surveys to try to probe the faint-end luminosity function. People really tried to do it all because people, I think, were scared, and I think rightfully so, that we wouldn't necessarily have years and years of JWST time to do what we needed to do with the high redshift universe and answer these questions. So I'm glad we're not in that circumstance, but I think it did reflect a little bit the strategy that people took heading into launch. Now, the first results from the SMAG, I'm taking a bit of a historical perspective because I want to get across that we were not first. I was not first when it came to finding these very high redshift galaxies. I was not first. You know, I think people really love to talk about, oh, you know, we were first in finding this. I wasn't first, and I'm trying to explain why. In part, I was not first. So, you know, the initial observations, the SMACs, this was amazing. I was blown away by these observations, just unbelievable. And, you know, the thing that really struck me, of course, was not just the images, but also the slit spectroscopy. And, you know, so Sandra Takela, Ben Johnson, and I, we did look at the properties of some of these galaxies along with many others. And we were just kind of getting our toes wet. We did not have our data. JADES didn't execute until the fall. This was the first data set, this, you know, with the early release science, where I felt like I could actually look at these objects and write a paper about some high redshift objects where I wasn't going to scoop somebody. I thought that was really important, actually, because, you know, this was something where people had been working years to develop their science program, to actually execute on their science program, and to make discoveries. And I had been working years in developing my pipeline for the GTO survey. I could analyze their data, but I didn't want to do that because I thought it was important to stay away because, you know, it just would not be right for me to do that, I felt. So, so we looked at this, you know, we looked at the spectra were just amazing. I was blown away. You could see oxygen 3 in a galaxy at redshift 8.5. Just incredible. You know, just remember the wonder of looking at these things. This was less than 3 years ago, or a little over 3 years ago. It was just amazing. And then this work here at Castellano, I thought this was just simply amazing. I felt this was very convincing at the time. This was July 19th. This was almost immediate. It was very convincing work, and then of course, it was confirmed spectroscopically later on at redshift 12.3. And this was, you know, something where once I saw these observations, I was convinced that, you know, something was going to change and there was going to be a lot out there for us to discover. Of course, I had huge FOMO. You know, I had massive FOMO on this, but you know, I said, look, you know, our time will come. It'll be fine. This was really amazing. And of course, these weren't spectroscopically confirmed at the time we got our JADES data. And so that, you know, these were still candidates at that time. I thought the CEERS data was really an important effort, and I thought they tried really hard to produce a data set that the whole community could use. We were interested in looking at the CEERS data. We did look at the CEERS data. I didn't publish anything on high redshift universe with CEERS. I did look at AI, machine learning analyses of the CEERS data because I had looked at the candles data, and actually with Ryan Housen, who's here in the room, we did some initial AI machine learning on some of the initial CEERS data. But again, you know, when I saw so I'll skip over this, not that important. You know, the Maisie's Galaxy with Steve Finkelstein that was also later confirmed by Pablo, it was just a sense of wonder, and there were so many papers that came out. I listed Sandra's paper from earlier. I shouldn't have listed that in this context, but there was just a lot of excitement. A lot of the data was coming out, but I was salivating. I was like, how are we going to, I just was very excited. You could tell I'm still excited about it. Okay, so, right. And then there was this. And so, with the lead up, with all of these candidates, none of which had been spectroscopically confirmed, there was the redshift 16, above redshift 16 candidate in Sears. And this was a galaxy that pretty much everyone could go and verify, and it's a real thing. It's a galaxy that exists in Sears. And we looked at it, within JADES, we saw that it was there. And some of the people, in JADES are also in connection with some of these things. So this was a completely plausible candidate, and they did a great job in their analysis, right? Given the models that they used, this was a good work. But there are limitations, and this is something that we pulled away, straight away from the JADES data, and it had to do with the coverage of the filter set used in Sears. When we designed JADES, and I'll say a little bit more about the design JADES, I'm gonna have to pick up, we included medium band filters because we felt as though it was essential to be able to rule out low redshift interlopers that had strong line emission that look like high redshift candidates like this. And you may remember that here's the same analysis from Rohan Naidu et al. This is a high redshift model, just like what was in the previous paper. But if you include strong emission lines, you can fool yourself into thinking this is a high redshift galaxy when actually, if you include the emission lines, you see that it's a low redshift galaxy, and this was confirmed to be at low redshift later on. So, it is very promising, of course, to go out and measure these photometric candidates, but you need very deep data, and you need as much filter coverage as you can possibly manage. You need to design the filter set to answer the question that you want to be answered. And this was the best that we could do with Sears at the time, but we wanted to do a little bit more with JADES. So JADES is a collaboration of the GTO teams between NIRCam and NIRSpec primarily, but also the US MIRI team, and there are amazing collaborators in the US MIRI team on the within JADES. It's primarily imaging spectroscopy in GOODS North and GOODS South, designed to study galaxies high redshift to cosmic noon. There's imaging about 290 square arc minutes. In many NIRCam filters, the 8 to 10 is undershoot now, including broad and medium band filters. There's multi-slit exposures over 2 deep pointings that go very deep, and many medium exposure pointings to tens of kiloseconds, then some shallower exposures. And then there's MIRI imaging at 7 microns, but there's also some additional MIRI imaging that's been supplied by George Ricci as well. There's a huge number of people. I forgot Pier Luigi in the room when I made the slide. I'm sorry, Pier. I just want to highlight the steering committee, the people who lead JADES. That includes myself, Daniel Eisenstein, Emma Curtis-Lake, Andy Bunker, Stefano Carniani, Francesca Eugenio, Sandra Tikella, Marcia Ricci. I also want to highlight my students, Petra Mengistu, Courtney Kira, Anavi Upal, my former student, Ryan Housen, and there are students here. So Ryan actually works at Johns Hopkins now, and Courtney was an undergrad here, and they're now at UCSC. So there's a lot of great people in JADES. My main collaborators within JADES are Sanjo, and actually Ben Johnson is kind of the person I work most closely with, and then Kevin Heinlein at Arizona as well. Okay, so this is an image that shows the layout of just the JADES imaging. So in GOODS North, in spectroscopy, in GOODS North and GOODS South, there are many programs. And so for what it's worth, in the future, I will show you collections of data that include non-JADES observations. These are the JADES only observations to show you the layout. Okay, so the red here is NIRCam imaging. These are NIRCam parallels to NIRSpec observations. You can see it kind of looks like a mess, okay, but this is the nature of the beast when you want to do parallel imaging and spectroscopy. So we did our best to try to put NIRSpec on top of NIRCam when we can. There were HST selected observations that then put out some outrigger NIRCam observations in various places, some of which are extraordinarily deep, including this area here, which later became the JADES Origin Survey. And then in Goods North, the imaging is somewhat shallower, as is the spectroscopy, although there is some additional IFU data on top of GNZ11, which is very, very deep and has now had some medium band data that other people have taken. I want to give you an example of some imagery, and I will share some more with FITSMAP. So one of the nice things, and something that's changed completely the way that we do science, is FITSMAP, which is a software package that Ryan Housen here in the room wrote. We load all of our images into an interactive website. This allows us to see all of the different multi-band images that we have, along with our spectroscopy and our catalogs. And in fact, if you want to whip out your cell phone, here is a QR code that takes you to the public FITSMAP, where you can actually view some older images that we have with some catalogs. Our public FITSMAP, we're actually gearing up to release a new version, which I think may be the final, although we're not sure, data release in JADES. It should happen in the next few months. That data will include a huge amount of new imaging. The spectroscopy will actually be released sooner than that. There will be a public spectroscopic release relatively soon, in the next few months as well. All of this data will be made completely public, reduced with catalogs, and be made available to you. So that should be helpful. I just wanted to give you a few examples of what the data look like. Here is HST, this is 850, it's 814W imaging of a galaxy. And you can see there's not much there. This is a very deep image, but you wouldn't look at this and say there's anything particularly spectacular about this galaxy. But then when you look at it through JWST, of course, you see that there's an amazing grand design spiral galaxy there. It's just, I mean, it's not fair, but we're not here to be fair. We're here to enjoy JWST. You also see, of course, you know, space is not empty. There are these amazing line of sight, you know, chance coincidences of galaxies where it just seems like they're stacked on one another, which is just remarkable. This is an example of, you know, loving art and not the artist, but this is a galaxy my wife looked at and says, oh, it looks like the Golden Snitch. But this is, you know, hierarchical structure formation writ large. Just you go in the universe and you see low surface brightness features in galaxies that are shells that show you one galaxy, you know, consuming and growing through the acquisition, through the accretion of another smaller system. And you see this all the time. Plus you see here, you see nuclear activity very often. When you see this kind of structure, you see the association between the evidence of hierarchical accretion with nuclear activity. It happens all the time in these images. And then, of course, the cosmic rose, which everyone loves. Stacy Alberts, I don't know if she's here, she made a very nice image of the cosmic rose, one of the first ones. And, you know, we're all a bit romantic. Many of us are, some of us aren't, but I am, I try to be. You know, and this is just an amazing, you know, dusty merger with a galaxy that has some line emission that happens to look green in this image. You know, it's something that we can all still appreciate the beauty of these images without then trying to scour them for the highest redshift galaxy in the universe. That takes me to, you know, oh, sorry, no. Another thing that's really amazing is you can actually see with these multi-band images, you go and you take these images with, you know, very densely in wavelength, very dense sampling in wavelength. Here we have 115, 150, 200W, 277, 335, and 356, 277, 335, 356, 335, 356, 410. You can actually see line emission by eye. You can do photoz's by eye if you know where to look. In these, you can see, H alpha, you can see O3, you can see H beta, O3, you can see H alpha, N2, you can see Passion alpha at redshift 1 in this galaxy by eye. It's amazing. This I made this picture for one of Daniel Eisenstein's papers. It's just remarkable what you can do with this facility just with the imaging if you, leverage the design of the instrumentation, which is great. Okay, and then I couldn't, not show this. So Bob, one of the true undertakings that this institution really pushed forward and, established this field of looking deeply at the sky. And of course, now with JWST, we've, this is in Goods North, and you can see the same area of the sky with JWST. And the stretch of this image is meant to try to mimic the HDF. It's not trying to be a press-worthy image necessarily, but you can flip back and forth, and you can see just how much deeper in surface brightness, the JWST image goes. It's, amazing. So it's something that I have a lot of fun looking at. Okay, I want to go through quickly how we actually do some of the nitty-gritty details in JADES, and then I'll get to finding some of the highest redshift galaxies. So we have a lot of observations in JADES. We take many multi-band images. We take them at different orientations on the sky, very different position angles. So we have different subregions that are executed at different times of the year with different position angles, with different filters. What we do, we actually look at every single exposure that we take by eye. The way we do that is by building these GIFs, okay? So we make animated GIFs of each exposure sequence, each dither pattern. You see one of them here. We do that starting with the raw images, then we go to calibration as a frame, a panel in this GIF, then the background removal, and then masking, which we mask individually each set of dithers by hand. Okay, so when we see scatter light features that are persistent between different exposures, we mask them by hand. Okay, you can see this one's moving here. There are many customizations that we make to the JWST pipeline. We don't use we use it, we live and die by it. Obviously, it's something that is essential for us to use, but there are many components that I am going to share with you that we do change in the JWST pipeline to make it work for us, okay? We do our own tweak astrometry. We do our own background subtraction. I wrote the 1/F noise correction that we use. We use our own non-negative matrix factorization WISP subtraction. We make our own flats. We manually mask every exposure. We do our own outlier rejection, and this is actually something we know we learned recently is something we're going to communicate with you all about sometime soon, I think. We also do our own custom inverse variance weighting during the final mosaicing. So each one of those steps, we do something different than the standard JWST pipeline does. And there's reasons for each one of these that when we have our new set of data products, we're going to go into some level of detail, but I'm happy to talk with you individually about if you're interested. But I wanted to mention these because I do think it's important to talk about, especially with the experts here. I'm going to talk a little bit more about what happens after we get exposures that have been calibrated and background removed and masked, okay? So this is what all of our mosaics look like. This is just good south here. We have 070, 090, 115, 150, 162M. 182 F200W, you can read all of them yourself. There are many different programs that are included here. I'll say more about that in just a moment. This is not just JADES data. The deepest data here is not our data either. We have the most time that has been spent here, so the majority of the time that goes into these images is from JADES, but not the deepest data, not the largest area, although most of the time here is spent in JADES. Okay. So then what do we do with all of these individual mosaics? Well, we have to find the galaxies. So how do we do that? Well, we build a detection image, and the way that we do it is we build a long wavelength channel image. We do a long wavelength stack that's an inverse variance weighted stack. This is what our inverse variance weighted stack looks like, which is the collection of all these individual long wavelength filters that we add together in a inverse variance weighted way. Now let me give you some sense of what this looks like. So here's an RGB image. This is, you'll get accustomed to seeing this. This is from the FITSMAP viewer. It's just very convenient to go and look at various parts of the sky. You can see that this is going to be complicated. There isn't anything easy about this, because as soon as you go as deep as you go with JWST, as you know, you start getting confusion, right? How do you pick apart these galaxies? We have to do deblending. And the way that we do deblending is by building a deblending image around 2 microns. We use data around 2 microns to do that deblending, okay? And we've built a special custom algorithm to do that deblending, which relies on the shapes of peaks in the light distribution around 2 microns, okay? This is what the detection image looks like. This is very highly saturated, so this is going as faint as possible. You can see that the noise, and it doesn't look that way on this screen, but actually the noise looks very Gaussian at low levels here. This goes extremely faint. Okay, this is a very, very faint stack. We're talking noise levels that are, 0.1 nanojansky kind of RMS levels in these detection images. Okay. Now I can go and take the log image for a different stretch just so you can see what it looks like. Yeah, there are things there. It's not all completely blended together. We take then a 2 micron stack and try to dissociate some of these objects. This is what it looks like when we actually break them apart and do the deblending. And here I've highlighted some typical apertures in many of these objects. You can see that the aperture that I picked here does not cover the full spatial extent of the low surface brightness flux around that object, just out of hand. Okay, so you do have to be careful about what you call the edge of these objects for some kind of aperture measurement. All right. Then you can do photometry on these objects, just, aperture photometry. But then how do you estimate what the uncertainties on your photometry are? This is important because you both want accurate photometry, but you also want to know when you can't measure the photometry well. This is important for finding high redshift galaxies because the blue filters, you're reliant on knowing what the signal to noise upper limit on the blue filters are, right? Because they drop out of the blue filters. Well, this is again something we're doing in a way that has never been done before. The traditional methodology for doing this is you lay down random apertures in your image and you measure the RMS scatter of flux in those random apertures. Okay, this tends to be an extremely noisy estimate of what the local noise in your image is. We don't do it that way anymore. What we do is we actually construct, since we construct inverse variance weighted estimates of what our single pixel level noise in our image mosaics are, we can actually do a joint fit using that estimate of the single pixel uncertainties as a template. We make RMS noise maps for different size apertures, and then we do a joint linear least squares fit of our uncertainties for all of those apertures and the single pixel uncertainties all at once. And then we generate maps that look like this that tell us at any one location, what is the typical uncertainty on our photometry. So we actually get very sharp delineations between regions that are very deep and regions that are very shallow. And that's important because these fields are complicated. We have extremely deep observations in the middle of very shallow fields. And if you just lay down random apertures, you mix together, bad and good photometry in a way that can be difficult to disentangle sometimes. There are tricks people have used, but this is the best one that I've seen to date. Okay. There is, of course, and just a second, let me get some water. A big issue in crediting people in our community. So you have a field like you see on the left, Good South. This is F444W. This is the collection of many different programs. How do you give credit to all of the effort that people expended in building a program like this? It's a huge amount of work. Each one of these individual programs, planning the design, making the individual data public. Okay, how do you credit that appropriately? Well, at the very least, you should tell everyone, well, we use these individual program IDs. But how do you know if I find the highest redshift galaxy in the universe here, what programs contributed to that? Well, it turns out to be very messy. So here, you can see each color represents a different unique combination of programs in Good South. And what we did is we invented a bit hash where we encoded the combination of all of the different programs that contributed to each individual pixel in our Good South image. And now we make this image and we report in our catalogs the bit hash that will, when decoded, tell you each individual program that you should cite if you use the data corresponding to that object or that region of the sky. This, I think, is the only way of really crediting appropriately the data associated with a very complex field like Good South. That is the amalgamation of many people's efforts. There's also a new thing that we're doing that, I heard people talk about ideas like this in the past, but I've never seen it implemented before, and we call it dynamic subregion mosaic masking. So we have a lot of, I showed you we have individual exposure masks, but we also collect together individual subregions from programs that are at different position angles. We keep them separate at first because when we build common PSF images, we have to keep different position angles separate so that when we build different convolutions together, we don't mix together the complicated PSFs that would beat against one another with different diffraction spikes, okay? So instead what we do is sometimes we have to mask those individual subregions separately. Now imagine what happens if you have stars that are observed at different position angles. You get stars that look like this, where you have diffraction spikes at different position angles. What do you do about that? Well, it turns out there is good data underneath those diffraction spikes. What if you could get rid of the diffraction spikes by masking only the diffraction spikes that have good data underneath them? Well, we do that. So what we do is we build a diffraction spike mask. Now, they're all stacked here, but we do that only in the subregions when those diffraction spikes exist at that position angle. And then we can erase the star. We can actually get rid of the diffraction spikes. And then we can do our photometry on the cleaned images underneath them. So something like Roman, when people are talking about doing many different position angles for the high latitude time domain survey, something like this is going to be essential in order not to be swamped underneath some fraction of the total sky of stars with diffraction spikes that eat into the observable part of your survey. So it's not perfect, but we're getting this process started. The last thing I wanted to say on the technical side, and then I'll spend the last bit of the time talking about some of the highest redshift galaxies again, is catalog curation. We don't do a perfect job. Oh my gosh, this is so hard to do. And you can see this garbage. I failed, So what do we do about that? Well, Ryan, because he's so good at this, we came up with a way where we can actually curate our catalog on the fly. So there's a way of going in and actually editing our catalog. We build polygons around our catalog. We can select the objects in our catalog that we want to merge, and then we can just eat them up and merge them back into the main source. And we just submit that into a web form, basically. And then when I rebuild our next version of the catalog, it gets merged back into some source that we can pick. So we can actually go through the process of curating, because you're never going to get it perfect. Now, where this comes, you have to be a little bit careful is for completeness simulations, that is a problem here. But you don't do this willy-nilly, you do this in regions where you don't care about these things, and you don't care about them. Around other galaxies and stuff, you have to be a little bit careful. But it is worth doing in diffraction spike polluted regions. All right, so then you wind up with a beautiful galaxy, and you want to find the high redshift galaxies in those. And the first set of these early galaxies, some of these galaxies, of course, were known. They were known from the original Hubble Ultra Deep Field stuff that Massimo was heavily involved in, and then UDF-12 isolated one of those galaxies to be at even higher redshift that was originally anticipated, and that galaxy then turned out to be at pretty high redshift, above redshift 11. But we did find in JADES 2 additional galaxies, both of which were above redshift of 12. And those galaxies, along with the others, were then spectroscopically confirmed in Emma Curtis Lake's paper from JADES as being at actual spectroscopic redshifts above redshift 10, which was, to us, just something amazing. And of course, some people in the room know that this was kind of a fluke because there was a short in NIRSpec. Otherwise, these things would not have made it onto slits. We could only have observed these objects because there was they weren't originally planned to be on slits, but there was a short, and then we could open up slits because of the replan. And we got slits on them, and they turned out to be at high redshift, so that was wonderful. I'll skip ahead here. That was the press thing. Now, we went back and we added additional data. These are extraordinarily deep additional spectra that we took as part of the JADES origins field. And you can see 270,000 seconds of time and 2,000 seconds of time. Note that the redshift of this one came down quite a bit. The redshift of this one did not change at all. There's no evidence of lines at all in this redshift 13.2 galaxy. Okay, and there's also no evidence of additional damped Lyman alpha around this galaxy. There's no Lyman alpha. There's no damped Lyman alpha in that galaxy as far as we can tell. Okay, so that's very interesting. So there's not an excess of neutral gas in front of this galaxy. There's also no Lyman alpha from that galaxy. It's amazing what you can do with that amount of time. We also did a lot of work in trying to model the detailed properties of those galaxies. As you could see, those galaxies were extremely small, essentially unresolved. So how do you model unresolved galaxies? Well, you have to do forward modeling of those galaxies to put any constraint on what their structural properties are. And we do that with a code called ForceFo that Ben Johnson wrote, where we actually forward simulate all of the objects that we see potentially in that field. We vary their size. We do full Monte Carlo simulations. We try to then back out what we think the true photometry associated with those sources are. This allows us then with also using a model that Ben wrote called Prospector that does SED fitting. Ben does a lot for this community. We fit stellar masses, star formation rates, and ages to these galaxies. They're extremely young, less than 100 million years, only a few tens of millions of years. They're forming stars at a reasonable rate, solar mass a year. They only have maybe 10 to the 8 solar mass in stars, although there's a large spread. And so, they're pretty young. They're extremely small. They're very compact galaxies. That also means that their dynamical timescales are short, only a few tens of millions of years. So the fact that they're young is maybe not so surprising because the densities are very high, the timescales are very short. Okay. Then there's GNZ11, which again was a galaxy that was known from GRISM spectra to be very likely at very high redshift, probably around the redshift 11, and turned out to be redshift 10.6 or something. This is this observation or image from Sandra's paper that I made. You can see the cutout of GNZ11 here. You can also see all of these high redshift candidates around GNZ11. These objects have not been confirmed or observed spectroscopically as far as I am aware. A lot of things seem to be at high redshift around GNZ11 that are pretty close by. That's pretty interesting. Okay. The one thing I think that took my breath away more than anything else in the first year of observations, first year and a half, was this spectrum. I could not believe the quality of the spectrum. I mean, it was a very bright galaxy, but all of the different lines that you saw in GNZ11 were absolutely stunning to me. And, you know, people, of course, debate whether GNZ11 has a supermassive black hole. It's not that super, you know, it's 1 million solar masses if it's there. But if it is there, then it is growing at a remarkable rate, probably had to have been growing at a super Eddington rate for much of the age of the universe before it was observed, only less than 500 million years after the Big Bang. Otherwise, it could not have been there. And through pure Eddington limited growth, it's very difficult to explain given the models that exist. Okay, and that takes me to the JADES origin field in the distant galaxy candidates, although as you'll see, some of these objects have been confirmed from my paper from this last year. And you know, this was something that to me was just absolutely like a huge undertaking, mostly because I found it very difficult to believe. Whenever you make an observation and you yourself are like, is this really something that you believe? And you're like, maybe. And you know, the thing is, you may have noticed that this paper, between the first issue of the paper on the archive and the accepted version, changed. And it changed because one of these galaxies was confirmed spectroscopically. And I will explain that why it happened that way. So, so what did we do? We actually, in the region of Good South, we took additional observations with medium band data. This is extremely deep additional data with 162M. I only have a few minutes. And this data allows for us to look for galaxies at the very highest redshift. And in fact, I'll have to skip ahead. What we did is we you know, did a veto and looked for galaxies above redshift 11 and found galaxies that looked like they were at redshift 14.4. And this galaxy here, this galaxy was later spectroscopically confirmed to be at redshift 14.2 by Carniani et al. Through JADES. This galaxy, you can see, is actually behind another galaxy that's at lower redshift. This is one of the reasons why we were very tentative about this galaxy. In fact, we were not even sure we were going to put a slit on it because it was suspicious because it was by this other galaxy at lower redshift. There was also this other very interesting galaxy here, which our SED models showed that it needed Lyman alpha emission to explain its SED. And everyone in the collaboration, almost everyone, said, that can't happen. That galaxy does not have Lyman alpha emission. It's at redshift 13. We then followed it up spectroscopically, and of course, it had Lyman alpha emission at redshift 13. So there were many surprises, and let me try to explain a few of them. What you can do is you can go and you can count up those high redshift galaxies. Okay, and these high redshift galaxies, you can just simply take the survey, you can do simulations exactly the same way you do the observations, and you can say, how many galaxies would I expect, how many did I observe? And you can try to use that to constrain the number density evolution of galaxies as a function of redshift. You can then compare that with the abundance of dark matter halos as a function of the mass of dark matter halos. Okay, so these are 10 to the 9.4 dark matter halos. These are 10 to the 10, 10 to the 10.4. And you can see that the number density evolution of galaxies is not falling off nearly as fast as the number density evolution of dark matter halos. That means that galaxies at high redshift, you have to continuously remap dark matter halos and galaxies as you go progressively further back in time. Galaxies have to get in lower of a given mass, a given luminosity, have to be in smaller and smaller dark matter halos in order to get the numbers to work out. There has to be a continuously higher and higher efficiency of galaxy formation at earlier and earlier times. Otherwise, you would massively overpredict the number of dark matter halos of a given large mass if you keep the mass of a dark matter halo fixed. This is very familiar to me. I have triplets. This is them in 2009. I'll end after this. You know, they were born earlier than I thought they would be. There are more of them than I thought there should be. And they grew to be bigger than I had expected. So yeah, this is a very reminiscent problem. Anyway, so yeah, thank you for your time. I'll go ahead and end the talk there. All right, thank you. Too much on the technical, not enough on the science, but that's fine. Thank you for your patience with the nitty-gritty details. Yeah.
And yeah, thank you very much. Yeah, I think your career arc to Observer is complete.
I can regress to the mean now, yes.
Thanks for sharing your techniques and exciting results. Good question. And I'll try to check online too.
Yeah, can I field? Mark was first, I think.
Yeah, great talk, really, and perfect ending to it, too. So I was really interested to see when you showed the isotopes and there's flux outside those galaxies. We have recently gotten interesting measurement of the cosmic optical background with New Horizons, where we find maybe 20 to 30% more light than predicted from the galaxy catalogs. I wonder if you have an estimate of how much light you might be missing due to that effect.
Yeah, so so I actually cut technical details out of this talk, believe it or not. So so one thing that I'm very wary about is putting too strong a term of what these isophotes mean. And part of the reason is that these are a cron-based isophote, okay? And actually, I have completely re-engineered the way that I'm measuring the outer radius of these objects. It's something that will go into the catalog paper. So you can tell that we go extraordinarily deep if I can get to the full exposure here. And so, you know, we could provide you with an estimate of that. I would be cautious though, because the way that people do background subtraction differs substantially. And the question that you're interested in answering, I think you would have to reprocess actually the whole data set to be able to address. We see over subtraction many different places in our data that we also see over subtraction when we use the regular JWST pipeline. We see over subtraction if we do it the way Sears does it. You know, it's just a difficult problem. And then you say you see an excess of background. So, you know, I think there's more to be done. I wouldn't take the isophotes or the ellipses that I showed you too literally there. Yeah. Yeah, Massimo.
Thanks for the great talk. I was intrigued by the GNZ11 field. Are those objects the candidates at this kind of redshifting? Did somebody try to take their spectra, or nobody tried? Because obviously seeing an association at that redshift would be very interesting.
Yeah, I agree. It would be very interesting. I mean, you know, people trying, and I mean, what does try mean? I mean, try means, did you get the time, or did you execute the observations? Yeah, no, I mean, I don't think anyone has executed observations on those objects. Yeah.
And if anybody online has a question, I don't see, but let's stick with the room here and we'll see online.
Yeah, Harry. Hi, Harry.
Yeah, so your last diagram that showed the sort of efficiency of star formation and halos. You know, the other way to look at that is, you know, it started out with the right efficiency and it's just gotten less and less efficient over time. But so if you put your theorist hat on and you say, okay, well, take that perspective, what's making it less and less efficient? Do you expect like one process to dominate, or there to be special epochs that we should go look for with JWST or something to say, you know, this is the epoch of supernova feedback, or this is the epoch of whatever? Yeah.
Yeah, I mean, I think that's an interesting question. I think that there, you know, I mean, one thing that we talk about in the paper is that in the JADES origins field, in principle, we are sensitive to galaxies out to redshift 20, and we didn't see anything. Now, that's probably a volumetric statement, and that's reflected by this, which when you go out to redshift 20, you know, blows up. And when it blows up, you actually don't know what this range of efficiency is, and it could be quite a bit. But by the time you get out there, the curves that you see here, they're actually extremely steep. They're almost vertical. Okay, so you can almost say nothing at that point. We know nothing at that point. I think that because the curves are so incredibly steep, yeah, it's very difficult to say how you peg yourself to that connection between galaxies and where the dark matter halos lie. I think, you know, by the time that galaxies, you know, in the luminosity function, I mean, this is the integrated number density, not the luminosity function. That's something else to keep in mind. You know, by the time you get to the point where the Milky Way is at the, you know, at the knee in the luminosity function and it's touching the halo mass function, then, you know, it's pretty easy to convince yourself, well, something feedback, you know, you buy yourself the baryon factor and a factor of 38%, and then you're in good shape. Here, you're talking about having to continually remap the efficiency over a time scale that's less than 100 million years. I mean, it's really a short amount of time for you to decide how to change the physics in the galaxies, right? So the things that can change on those timescales are the metallicities of the galaxies, provided you can mix, you know, the metals quickly enough within, they're small. The dynamical timescales are a few tens of millions of years, so it's possible to do that. But, you know, I'm gonna get into trouble. So, you know, the idea that we have this like feedback-free star formation in these galaxies, I think is kind of generally, I mean, it can only be so efficient, right? That is kind of generally true, but that is like a specific model. And it has a lot of like machinations to make it work. And undoubtedly those actually don't all work. And so then where are we at? And those machinations would all have to change differently over extremely short periods of time in order for this remapping to happen. So I do think that there are big questions lurking out here. That's why I try to leave it as general as possible in terms of this diagram. I'm not wedding myself to any particular model, except for a dark matter halos exist, and I've counted some galaxies, which I think is kind of the simplest approach to discussing what this issue is. Yeah.
On that note, it's just after 4.
Okay.
Brant is around for happy hour after this. There's also 2 slots for dinner. If you want to join, let me know. And Brant's around all day tomorrow with a pretty full schedule. But let's thank Brant again for next one.
I could not see you, and I was not paying attention to the time.
Yeah.
And yeah,
From the end.